Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's an honor to have Peng Dai here from the University of Washington. Peng is a PhD student finishing up this spring. He's been working with a close colleague, Dan Weld, over at University of Washington. We've known for many years. Dan and I talked years ago, I think it was at a banquet, at a meeting, about all this, what we considered ad hoc yet interesting crowdsourcing going on, and couldn't we do something to optimize it with some decision-making under uncertainty to make it more efficient, to route people to problems and vice versa. Peng has been working in this space. It's a very exciting and promising space. Peng did his bachelor's degree in computer science at Nanjing University, did his master's in computer science both at National University of Singapore and then at University of Kentucky. There with Judy Goldsmith, many of you know. That's what brought him to Lexington. And he's been working in the space of automated planning, decision-making under uncertainty, decision-theoretic optimization of crowdsourcing, and we'll be hearing from him today about some of the latter work. Thank you.
Thank you, Eric. So my background is decision-making under uncertainty, and my work is highly motivated by the lack of scalability of decision-making under uncertainty. And I'm fascinated by this real application that is quality control for crowdsourcing, and that is my topic today. So I wonder if any of you have dreamed that one day you're going to relaxing at your office and all your work has been done by somebody else. If that is your dream, then this talk is right for you, because I'm going to tell you how to do that. And the underlying technique is crowdsourcing. And crowdsourcing is a really new notion which refers to outsourcing tasks through open core to a group of unknown people. Although crowdsourcing is really new, it is growing very fast. For example, Crowdflower used crowdsourcing to do Haiti earthquake rescue. A game of purpose called Folded is to let game players to help solving large and complicated computational problems. A company called Smartsheet used crowdsourcing to extract useful information from the web. And Facebook used crowdsourcing to do natural language translation. So with the rapid growth of crowdsourcing, I would argue that it has a large potential market. So thinking of outsourcing is a notion that is introduced in the 80s and is boomed in the 90s. And nowadays, it has a large market size of over $300 billion. And crowdsourcing is only recently introduced a few years ago, and now it reaches a market size of over $1 billion. And it will be interesting and reasonable to estimate that one day it's going to have the same or the comparable size of outsourcing. Even if it only occupies 10% of the market, then it's still over $30 billion.
Where did that number come from, the crowdsourcing market? Do we know what Mechanical Turk is bringing in these days, for example?
Yeah, it's from a survey from the smartsheet.com.
How much is Mechanical Turk bringing in these days? I wonder. Anybody know the answer to that question?
How many?
This raw revenue of Mechanical Turk, I wonder how big that is.
Very little.
Oh, I think it's tiny.
Yeah. And is this? Do you happen to know if these numbers are sort of net transfer numbers or sort of gross? In other words, is it how much money a Smartsheet made, or is it like $1 billion? Some people paid $1 billion to some other people in aggregate, and then a little tiny bit was taken out off the top.
So notice that this number does not only takes into account Mechanical Turk. There are many other websites for crowdsourcing, and this is only an estimate. It's not an exact number. But
it's gross. In other words, it's like $1 billion
It's actually a net revenue for the entire crowdsourcing market. Yeah.
Cool. but that means that the people. Yeah, okay. Never mind.
This is
Go
good,
ahead.
not technical content.
Oh, okay, that's fine. I was just curious.
Yeah.
That seems unbelievable.
Yeah.
Okay. And if we can use some sophisticated mechanisms to, for example, cut 10% of the cost, then we're talking about billions of dollars of savings here. And Amazon's Mechanical Turk is probably one of the successful marketplace for crowdsourcing. And notice that at each time of the day, there are over 100,000 hits or human intelligent tasks available on Mechanical Turk. And there are two basic roles on Mechanical Turk. One side is the workers. So the workers log on to Mechanical Turk, finding the tasks that they're interested in, work on those tasks, and earn some money. On the other side is the requesters. So the requesters post their tasks, get their jobs done, and make a payment. So there are over 100,000 of registered workers on Mechanical Turk. So even with this ample human resource, people are kind of not using Mechanical Turk in a pretty conservative way because quality control is kind of hard. And here are some representative tasks on Mechanical Turk. So there are some simple tasks such as survey questions and data labeling. And for survey questions, people don't actually need to do quality control, but for some labeling tasks, people use duplication as well as majority vote to guarantee the quality. And there are some more complex tasks such as audio transcription, document reviewing, document writings, and things like that. To do quality control on this kind of tasks, people use workflows that enable workers to improve and evaluate each other's work. So these quality control mechanisms tend to be very effective in practice. However, as a computer scientist, we ask ourselves, are those mechanisms good enough? For example, there are many interesting questions that we want to ask ourselves. For example, for the duplications, how much duplication is enough? And is really majority voting the best mechanism that we can achieve? For the workflow, is there any way to dynamically generate and control such a workflow so that we can get the best cost and quality trade-off based on the history of answers that we get? And in this work, we aim at answering all those questions. So we built the first decision-theoretic quality control system for crowdsourced workflows. And of course, our system is based on parameterized models. So we propose efficient mechanisms to learn the model of the system and plugging the learned model into an end-to-end system that achieves statistically significant better results. And also notice that our system is able to benefit from incrementally updating the model using the new data. So here is the outline of my talk today. So I've talked about the motivation of this work. And then I'll move on to quality control for simple tasks. That is, to do quality control for Boolean questions. I'm going to propose our worker model and difficulty measure and our mechanisms to learn the model and compare that with majority vote. And then I'm going to move on the quality control for more complex tasks such as workflows. I'm going to tell you how I'm going to build this decision-theoretic quality control engine for workflows. And there are many interesting related work. And I want to point out that Eric has done some really interesting and orthogonal work on decomposing tasks into workflows and find the best correlation of human and computer resources to complete these workflows. Whereas for our work, we kind of try to optimize a specific type of workflow. And I'm going to finish talking about future work and conclude. Okay, so I keep saying that quality control is hard, but why it is really hard? So we have hundreds and thousands of workers on Mechanical Turk every day, and these people are from different backgrounds. They have different expertise, they have different diligence level, they have different various motivations, they have different background, so it is really hard to do. And also, even if for a particular person, he might be multitasking, he might be tired, he or she might be careless at different tasks. So there are a lot of uncertainty at the time when the worker is completing those tasks. And the underlying intuition of majority voting is that even if any single worker is not very good in accuracy, if all the worker answers are independent and they are all better than random, then doing majority vote on these people is going to achieve better results, better accuracy compared to individual workers. And indeed, Ryan Snow shows that the majority vote of an average 4 workers can achieve the same accuracy level as an expert in natural language annotation tasks. So when we approach this problem, our first intuition is that the workers are really independent. However, after second sort, we feel that it is not, and the reason is follows. So let's think of a task of which object has a bigger size. If I give you these 2 objects, then pretty much everybody is going to give me the same answer, which is the left one. However, if I give you these 2 objects, then the answers might be divergent. So the reason being that the left one is really easy, and the right one is hard. So the workers tend to give you dependent results because of the hardness of the task itself. And so we model the intrinsic difficulty of a task through a parameter called intrinsic difficulty, D.
I don't understand. Why can't the workers be independent on the hard task? Let's say they're just half of them say circle and half of them say triangle at random. Why would they be correlated?
So their answer itself is correlated is because more or less people are going to be, their answer is going to be divergent. Whereas if you're given them an easy task, then maybe 90% or even higher number of percent of people is going to tell you left one is the right answer. So their answers are not independent given the task. Their answers are independent given the task, but not marginally independent.
I guess again, why would a hard task not be given the hard task? Why would it not be just a coin flip?
That's right. So that is actually our intuition. So their answers are independent given the task itself, given the difficulty of the task. But without the difficulty, their answers are not independent, because the problem itself can be easy or hard. And
you're saying it's the opposite. The easy one is not independent. The hard one is independent. It becomes a coin flip. That's right. That's what you were saying.
Yes.
Yeah.
Yes. Oh, okay. There we go. Okay, that makes much more sense.
Yeah. So instead, we have this conditional independence, which is the worker's answers are independent given the difficulty of the problem. And now we have this difficulty, and we want to find out what is the probability that a person answer a question correctly. So let's use a Boolean question example here. If the problem is really difficult, if the problem is really easy, then that means the difficulty is 0. Then everybody should answer the question correctly. So that means the probability should be 1. And to the other extreme, if the problem is really hard, then the probability should be 0.1, because the better we can do is a coin flip. And these 2 cases are really rare, and they don't usually appear in the practice. And what we're really interested in are all the intermediate cases. So we use this family of functions to model a person's accuracy. And we introduce this gamma, which is the error parameter of that person. So a good voter typically have a smaller gamma, whereas a bad voter typically has a larger gamma. Yeah.
Are you right now treating the error as just defined as Bernoulli variable? Or are you going to be looking at, for example, categorical tasks, and you will have a distribution for error across different categories?
So for this example, we're just talking about Boolean questions.
Okay.
Yeah. So now we have this error parameter for every single person, and we want to figure out what are the exact values of these error parameters for people. So here is our learning task. And this is a typical plate notation for graphical models. And this typically says that we have m Boolean questions, and we have n voters. And the capital gamma refers to the unknown distribution error parameter distribution of the entire population. And a small gamma is the error parameter of a particular person, particular voter. And it is dependent on the capital gamma. And B here refers to the answer of a person to a particular question. So we know that the answer of that person depends on 3 variables. One is the error parameter of that person. Secondly, the difficulty, D, of that question. And lastly, V, which is the truth value of that ballot question. Is this clear?
What was capital gamma again?
Capital gamma is the underlying error parameter of the entire population.
Prior for.
It's like a prior, yes. Yes.
Your D and V are shaded, but aren't they unobserved?
Yes. So for this learning task, we assume that they are provided by human experts. So we're using supervised learning here. Okay. Yep.
In many of these tasks, you use the voting to get to the right answer, right? The task owner doesn't know the correct answer, and you are doing majority voting to kind of discover what the correct answer is. So you really don't have the ground truth to be able to evaluate the error.
Right.
So how do you solve this problem of not being able to know the ground truth to be able to evaluate the error metric?
Okay, that's a good question. Actually, for those questions, we don't have the ground truth. We can instead use unsupervised learning. And I'm going to tell you about another related work on unsupervised learning. Is that?
I think my question really is, the problem can be very difficult. So the answer is wrong. And then your unsupervised algorithm will tell you that this problem is in fact easy because you get to an answer really quickly, although the answer you get is wrong and the problem is really hard. So even your unsupervised learning algorithm wouldn't be able to capture scenarios like that. So do you have any assumptions like it works if you can get to the correct answer by doing majority voting?
So no. So we're assuming that the answers are provided in a way that should be aligned well with the model. So using unsupervised learning algorithm, we assume that the learning algorithm is going to tell us, based on their inference rules, what are the correct answers. I know this kind of questions are sometimes subjective, and there is sometimes really no correct answer. But let's assume for now that we do have a correct answer, which is either known or unknown to us, and we're going to figure that out.
I think your question is more going towards the previous slide where you actually had this model. I think you're saying that there might be questions that are in fact hard but appear to have an easy answer. So even though it's in the very hard side, people do agree on an answer and it's wrong.
If you don't have the ground truth and just depending on the collective answer, I think that will be a problem in evaluating how hard or easy questions are.
Okay, so we picked this image description task. So what we do is that we give a person an image and let that person write an English description which describes the picture and better distinguish that picture from similar pictures. So this is a Boolean question. We give them 2 English descriptions and ask them which one is a better description. Okay? So we assume that we're getting the Boolean answer from the workers. Of course, we assume that we're going to get the actual truth values and difficulties provided by the human experts. And our question is, how good each voters are. We want to figure out the error parameters of all the individual workers. And our solution is a maximum a posteriori estimation. Yeah.
What's the highlighting about?
Oh, the highlighting is the difference between the 2 paragraph wordings.
Then they're presented with the highlighting as well.
Yes.
Something that I don't understand here is you make the assumption that there is a right answer, and that if someone provides another answer, it is wrong. Whereas when it comes to things like that description, it might be that actually 70% of the population prefer this description and 30% prefer the other description. So there is not exactly right and wrong here. There is a matter of preference.
Sure.
So can you explain it a little bit? How do you see that?
Yeah, that's right. So as I mentioned, that these questions are sometimes very subjective, and there's no right or wrong answers for that. But let's assume for now that we do have a Boolean answer for those questions.
So you assume that there is a correct answer, an incorrect answer, and whomever says the incorrect answer is wrong. So there is no matter of preferences or multiple meanings or stuff like that. There is just right and wrong.
Right. Yeah, that's our assumption. Yes. Okay. And here is the learning results for the Ballot model. So we give 20 questions to those people, and there are 45 voters at total. And we're comparing two mechanisms. One is to use the majority voting, and the other is to use the Ballot model. And they both achieve the same accuracy, which is 80%. However, we figured out that in reality, we don't have the luxury to ask 45 people for the same Boolean question. So we randomly sampled a subset of the votes for the people, and we compare the two mechanisms. Now we can see that using our model is actually outperforms the majority vote significantly, consistently. And using only 11 votes, we can achieve an accuracy which is very close to using all 45 votes. And also, we can achieve the same accuracy by using only 5 votes comparing to using majority vote for 11 votes. And that means we can save over 50% of the money. Okay, and of course, if you don't know the ground truth of the difficulties and the truth values for those questions, you can use unsupervised learning. And Whitehill et al. They use this interesting unsupervised learning algorithm. The advantage is that there are no gold standards data provided, and they show that their EM algorithm is actually pretty robust.
They have the same model, you're saying?
Not necessarily the same model, but the same look, same independent structure. Yes.
So as far as I recall, the key thing that they're providing is that they're providing the modeling of the biases of individual voters.
Mm-hmm.
And that's where a lot of the power comes from, is that they model both the biases with respect to different answers, as well as the kind of two modes where the voter is not paying attention or paying attention, and they have different bias models. And so the key results there were due to those two factors. So would you be able to introduce those in your model, and could we consider that? Or?
Yeah, that's orthogonal work. We can certainly consider all those factors into our model. Yeah, that's right. We can certainly incorporate all those things in our model.
Have you played with actually?
No, we haven't done that yet. Yeah.
But I mean, this brings up an interesting question, which is that so there's a per voter estimation or per score parameter like gamma, you can say, the reliability of that. But as you were mentioning earlier, and many other studies have found, is that somebody who's good for a while can decline in quality, not be good at certain questions. It seems like there's almost a per question parameter that you want to know about. I mean, I wonder if if you had some pre-test section with all these people and you figure out some value of gamma, is that really good enough to know for future performance of that person if they're going to be sufficient for your
Yeah, I think that's a really good question. So learning the temporal model for worker, as you mentioned, is really interesting topic that I'm going to pursue in the future. Yeah, that's exactly. Yep.
A factor that actually matters is the payment you are giving to the person. If you pay me more, I'll pay more attention and my quality will go up. Do you also consider those effects in this model, or is it possible to?
That's an interesting question. Actually, according to some work, I forgot their name, but Watts and I forgot the other person, but their discovery is that the quality of the answer does not necessarily go up with the price, whereas the response speed goes up with the reward. That's actually interesting observation.
Assuming the same population answering, but you can kind of classify your population and focus on a more qualified set of workers if you increase your criminal score, that may affect the quality.
Sure. That's another interesting thing to think about in the future. Yeah, Paul.
So maybe you'll get to this, but right now you seem to be assuming that workers have a sort of dominant scale of knowledge, that we're this good worker that is dominant across all examples to another thing, whereas people tend to be good in specific areas, right? And so this worker is maybe highly accurate in this area and not highly accurate in another area. So are you going to address that, or have?
Yeah, exactly. That's actually another future work that I'm going to talk about. How do we use the model for one particular task to another type of task? Okay. Yeah, that's actually the end of this section. Are there any more questions?
How did it work?
Yeah, this question also.
Did you do an evaluation of how well that worked?
So
Accuracies or?
So yeah, so this is actually our
The
evaluation.
unsupervised.
Oh, the unsupervised. I don't have their results, but turns out that their simple algorithm is actually performs better than majority vote. But I don't have the statistics on this slide. Yeah.
Oh, so you didn't actually do this experiment?
Sorry?
You did not do this experiment?
I didn't do this experiment. Yeah.
But what works great, the record, we have the code. The model is really nice.
Yeah.
So can you go back a slide? I think either I'm confused or I don't know. So you're doing the supervised, so you're assuming you know the answers to the questions, right? Did you look at if we only knew the answers to some of the questions and then estimate the difficulty and then see how well we would do on the rest or anything like that? Or did you, is this result just, is this that if they gave me 11 answers and I know all the correct answers, this is how accurate I can be? I'm a little confused.
Yeah, this is the using the cross-validation results. Yeah. So I train the data using part of the labeling data, and I predict the correct answer for the rest of the questions, and I. Yeah.
Okay. So this means you used 11 known answers.
Oh no! So I used. So I only picked a subset of 11 votes out of the 45 votes, and train that model on top of that, and I'm going to predict the performance of the rest results. Okay. Tasks, yes.
There's still the question of, are you just taking the 11 with the top gamma then? Or
no, random.
Oh.
Yeah.
Okay. I mean, it seems like there might be a question of optimal subset also, right? Like if you...
Yeah, that's the best scenario, but we tried a 10,000 random sets and calculate the average of that.
So you're not assuming any pre-information about what probably.
No, I don't.
You're just saying I just pick 5 at random. Right?
Exactly. Any more questions? Okay, so now I'm going to move on to quality control from complex tasks. How do I optimize workflows? And here is a task that is handwriting labeling. So I'm going to maybe give you half a minute and figure out what this handwriting is about.
It looks like my handwriting, actually.
Well, there you go.
Partial verification.
I actually did the figure, by the way, for these guys.
Yeah, so everybody can see that it is a really hard task.
I would refer them to a neurologist.
For tracking over time.
Yeah. And so what Greg Little approaches the problem is that he uses iterative improvement mechanism or workflow. So the idea is as follows. At every iteration, it gives an artifact which is a deciphered of this handwriting to the crowd and asks them, here is the current decipher of this handwriting. Can you improve this decipher for me? And after that, both the new artifact and the old artifact are given to 2 or 3 voters based on whether the first 2 agree with each other. And then based on majority vote, only one artifact is kept as a starting point for the next iteration. So instead of letting individual person working on this handwriting task, they just ask people to improve previous people's work iteratively. And that's the idea. So after 6 iterations, we got this very, very, very good decipher, which only got 4 words incorrect. And the part I like the most, which is that this thing really seems like a signature, but it turns out to be a score B-.
So how do you get the ground truth? You knew the person who actually wrote it?
They did the handwriting. Yeah. And they also used this iterative improvement workflow for image description task. And same idea. Everybody improve other previous people's description iteratively. And here is the first version of this description. And after 8 iterations, we got a very decent description of it. And that is the power of iterative improvement.
Seems like there's a strong potential for bias. Like the biases of each round are going to get heavily propagated, onwards. You can imagine.
Yeah, exactly.
You might want to start a bunch of these, at ground 0 at once.
Yeah, that's interesting. Yeah, to start from a different starting point and let people see how that pursues in the future. Yeah, sure. So Greg Little is an HCI person. When he came out with this iterative improvement idea, he didn't realize there are many interesting decision points on this workflow. For example, should I take another ballot? Should I perform another improvement? Or whether the description is good enough so that I should submit my current version. Whereas what he does is that he uses a static workflow which does not catch a lot of interesting dynamic cases. For example, if we have a good ballot people, and that means we might need fewer votes. And if we have a good improver, then that means we might need fewer improvement iterations. If, for example, we have a consecutive rounds of failed improvements, that means that the quality of the artifact is already pretty high. So,
what's the difference between a good ballot worker and a good improvement worker?
So the ballot worker is that if you give them 2 artifacts and let them choose which one is better, and that's a ballot question. And an improvement question is that you give 1 artifact and a picture and ask them, can you improve this artifact? Okay? Ballot question is just Boolean. So we use this dynamic workflow control, and here's our problem definition. So our workflow consists of a sequence of tasks which are either improvement or ballots. Okay? And our observations are the follows. We have a history of tasks that we have posted. We also have all the answers and worker information for all those tasks. And our decision is to dynamically generate the next task, which is going to maximize our long-term expected reward minus the total cost.
So each worker could participate in either one of those tasks? There are 2 separate populations.
Yes, each worker can choose to take any single task on this workflow. So this question is really hard because it is a sequential decision-making problem. The ballot answers are noisy, and hopefully we have already solved that in the previous example. So quality is unknown, and workers' improvement results are kind of uncertain. And to solve this problem, we refer to decision-making under uncertainty. And decision-making under uncertainty is a critical topic in artificial intelligence. For example, the robotics and automated agents are controlled by decision-making under uncertainty solvers and planners. It has been used to model a dialogue management system. And reinforcement learning techniques has been used to, for example, automatically control a helicopter. And of course, we use it to dynamically control a crowdsourced workflow. And here is our solution. We have a decision engine called Turcontrol, which has a model of the workers. And based on the model and history of the answers, our planner is going to automatically generate the next task. And on top of that, we have a learning algorithm that learns the model of the workers. So we're getting a problem from a person or the boss, and we return a solution to the person, and based on the quality of the solution, we're getting a reward from that person. To interact with workers, we post hits, human intelligent tasks on Mechanical Turk, and we're collecting answers from people and pay those people. So here is the dynamic workflow generated by our agent. Suppose we're given initial artifact alpha. Our first decision is that, do we need improvement? If the answer is no, then we simply submit alpha. Otherwise, we're going to generate an improvement hit, which give alpha to the crowd and ask the crowd to improve alpha. Then we get an improvement, which is alpha prime, and based on our model, we're going to estimate the quality of alpha prime. Then our next question is, do we need voting here? If the answer is yes, then we generate a ballot hit, which presents the crowd both alpha and alpha prime, and ask them which one is better. Then we get a result, ballot result B from the worker, and based on a model, we're going to update our quality estimates. And then we go back to the question, do we need more votings here? If the answer is no, then we're going to pick one artifact that has the high expected quality and go back to the very first decision. So it is clear? Comparing to...
What's the split up of voting into rounds? I mean, are you not... I get so confused because it seems like you could just submit if you have your alpha and alpha prime submitted to the population, they vote on it, and you're done. With that same alpha and alpha prime, why would you go back to do more voting on that same pair?
Oh, so this is just one voting task.
Oh, I see. So you have like one...
So you might want multiple voting.
I see.
Yes.
So you increase the number of people voting in
Exactly.
rounds. I see.
So comparing to a static workflow, our agent dynamically generates two decisions. One is, do we need an improvement, and the other is, do we need voting? Yes?
How do you control for cost? So you say if there's two opinions that just dramatically differ, and then every iteration you could just cycle continuously where your workers will say, well, the previous one is wrong, this one is right, and then in the next round the other judges disagree and so on.
Yeah, that's going to be captured by our difficulty measure, because if the questions really get divergent answers, that probably means that the question is really hard, right?
But which of the boxes here will exit out with a uncertain, don't know kind of answer?
I'm going to talk about that, but it's really hard to put all those things in a figure, but it's really captured by our decision-theoretic planning agent and model.
But which of the decision points actually will punt on the question?
Do we need voting? Do we need more voting? Because if the problem is really hard, then we probably don't want to go too much further because we're not getting any value here.
Wouldn't your improvement needed box need to submit the impartial answer then? Because you could go back then to improvement needed.
What do you mean?
To get out of the loop, it looks like you need to go to the submitting the incomplete or indecisive answer.
Oh, he's just saying that it's not. I mean, if that box, if the more voting noted box eventually says, okay, we're stuck, something's wrong. In the diagram you have, it seems like to actually finish, you have to go through that improvement needed box somehow. But maybe you have some other way of escaping out if the more voting needed is messed up or something.
So yeah, there's a mechanism designing whether we need any voting, and if we don't need any voting, then we pick the best one. And we're going to go back to the previous decision, do we need improvement, right? And a new improvement iteration is going to start. It's going to start from there. Yeah.
I think his question is, if a problem is really difficult and I stop and I cannot get an answer out, where do I get out of the system without consuming any more resources?
Yeah, it's going to be decided by our decision engine when we want to decide whether we need more voting.
What I'm saying is that to be able to get out of the system, the only place you can get out is the first decision variant, not the second one. So that's what I think he's asking,
Yeah.
right?
Yeah, that's. So the problem is actually determined by the decision-theoretic engine, and decision-theoretic engine is going to consider every single branch and then make the best optimal choice based on current results, and that is captured by the system itself. Yeah. Yeah.
So there seems to be an assumption here that you can actually make a decision at every point versus, let's say I was trying to get people to classify things into a hierarchy, right? Can you imagine at the top of the hierarchy there's a lot of indecision about which branch it goes into, and I kept getting back to this loop of more voting needed, improvement needed, because I can't decide which of the top things. But if I actually said, look, these are the one of the two feasible candidates, pursue these down and come up with the whole classification, now vote, when they see the full thing, they might actually be able to make a decision where they couldn't at the initial point. And so, like, how do you handle these kind of problems that once you actually follow it to completion, one of them just doesn't seem consistently to make sense? You can imagine translation that, you know, you were getting stuck on some initial word. If it was this, I think it's actually this whole thing. If I think it's this, but if I did the whole thing, suddenly it now doesn't seem to make sense.
Sure. Yeah, I think this might point to the problem that the system might get into like more local maximum or something like that, as you pointed out. Yeah, I think another thing is that whether our system is going to be able to do backtracking for some sense. Is that what you suggested? Is that right?
I would say you could think of it as local minimum, but you might think that you'd actually pursue each of them. There's some point at which it's just saying it's worthwhile to say, let's push these further see where we end up, and then see if we can evaluate.
Yeah, exactly. Yeah, so that in that case we have more decisions to make. Yeah, exactly. Cool.
I think one question I have here is the policy of this decision-making engine is always do one improvement, do the voting in a way that you always have two things to compare? Or can I have improvements, I have n possibilities, and then I do one voting along those n alternatives?
Exactly, that's exactly what you described. Yeah, that's the system. Yeah, the system actually works as you described.
Okay,
yes.
Because from this picture, it reads more like the first case where you do an improvement and do one voting.
So yeah, after improvement, you can decide we don't need any voting, so we can go back and then do another improvement. Is that what you?
Then you have multiple alternatives, not two.
Sure. Okay. And our system is able to estimate the quality of the artifact based on the model. So here is the model. We have some evaluation measures that we want to capture. For example, first of all, we want to define the quality of an artifact. We know that an artifact is of high quality if it is hard to improve. So we define a quality Q to be that an average person is going to improve that artifact with probability 1 minus Q. And of course, this is an unknown statistical measure and can be best estimated by random variable capital Q. And then we define the difficulty of a ballot hit. A ballot hit has two artifacts, one of quality Q and the other of quality Q prime. So we define the difficulty to be 1 minus absolute difference between the two qualities to some trained constant m. So this means that the closer the two qualities, the harder the task is. And of course, we have a reward function from the human or from the boss. That is his relative satisfaction with the quality of the artifact that we give it to him. And of course, we have some costs, which is the amount of money we need to pay to the workers. And our goal is to maximize the long-term expected reward minus all the total cost.
I'm sorry, where does M come from?
Where M from a training. So we model this problem as partially observable MDP, but I'm going to free you from the technical and mathematical details of POMDP, but instead talking about the key components of our model. So our system makes three dynamic decisions, that is 3 actions to take at every single point, whether we do another ballot, whether we do another improvement, or we're going to submit. And the transitions is coming from improvement, because after an improvement, we get a new artifact alpha prime with different quality q prime. And of course, this q prime is unknown, and we use this conditional distribution function to model an improver's accuracy. That is, the quality distribution of the new artifact based on the quality of the old artifact as well as the improver. And we have some observations in this model that is based on the ballot hits. So based on the ballot hits, we're going to update our belief distribution of the qualities, because that's going to give us some more information of the qualities of the 2 artifacts. And here is an illustration. So suppose our initial artifact has this distribution, and we do improvement, and we have an estimate of the distribution of the new artifact, which is like this. And suppose we are going to do a voting, and we came across a new distribution of the new quality, and replace it. Suppose we're going to do another ballot, and we update our qualities of the new artifact, right? And we replace it. And let's suppose that we do not need any voting, so we're going to compare these 2 artifacts. We're going to compare the distributions, and we're going to pick a better artifact, which is the one that has slightly better quality.
Or could you do that in the expectation?
Yes. And we're going to keep that as the starting point for the next decision, for the next improvement iteration. Is it clear? Okay. So planner. Our goal to do the planning is to make dynamic decisions, which is going to maximize our long-term expected utility. And of course, this is a too large problem to be solved exactly, because we have 2 continuous variables, q and q prime, and so the state space is infinite. And instead, we use an approximation algorithm to solve it. And we tried a bunch of approximation algorithms, and we find out the limited step look-ahead algorithm actually performs the best in practice. So the learner. So we want to learn how good a person is at improve other people's work. So here we pick 10 image descriptions, and we give all those 10 descriptions to 10 workers and let them each improve every description. So now we have 100 new descriptions as well as the 10 old descriptions. Let's say we're going to get their quality scores through mechanical Turk graders. And our learning objective is to learn 2 conditional distributions. One is the worker-dependent model, which is the quality distribution of the new artifact based on given the quality of the old artifact as well as the improver. And another one is the worker-independent model, which we do not have the worker information, but we assume that that worker performs average. That is the worker-independent model. So we're going to learn a 2-dimensional distribution, and this problem is kind of complicated, so we break up the learning process into 2 pieces. First of all, we're trying to learn the mean quality of the new artifact. And we assume that it is a linear function of the old artifact. And of course, this is approximation, but it turns out to be very effective. And the next step, based on the linear regression result, we're going to fit 3 distributions: beta, triangular, and truncated normal. So we have these 3 conditional distributions, and we want to find out what is the best distribution for our model. To do this, we use leave-one-out cross-validation. So we iteratively reserve data points, and we perform a linear regression on rest data points and a fit distribution. And after that, we're going to test the model based on the reserved data points. We do this iteratively for every single data point, and presumably the distribution that achieves the highest sum of log likelihood is going to be the best distribution. And our result shows that for the worker-dependent model, beta distribution works the best. Comparing with the triangular distribution, it has a higher peak. It is bell-shaped, has a higher peak in the middle. So this means the worker results are kind of stable. And for the worker-independent model, truncated normal works the best because comparing with a beta distribution, it has a slightly higher peak with same mean and standard deviation.
Is the truncated normal renormalized to integrate to 1 still in the truncation?
Yes, to 0 and 1.
No, but I mean, once you truncate it, it's no longer going to integrate to 1. And so if you evaluate log likelihood, you're going to get the wrong number. So
yeah.
you renormalize that to integrate.
Yeah, that's truncated normal. Yes. So this means that a group of workers' results are more stable than a single worker. Okay, so we now have the model. Yeah.
So you said earlier you compared it to UCT and other algorithms. Did the UCT experiment have a worker, like did you model individual workers or groups of workers, or was that averaged over all workers compared to, like I'm just trying to understand if your comparison, if you're comparing models that used detailed models of workers versus ones that only had an average model overall?
No, we compared them for the same background, so they have the same information for the planning algorithms. Yeah, they're built on the same model, same set of models. They have both the worker-dependent and worker-independent model. Okay, so here are the parameters of our execution. So we pay each improvement 5 cents. We pay a ballot 1 cent, and our reward is $25 times Q, times the quality. And if we encounter a worker that we have his model, then we're going to use worker-dependent model. Otherwise, we're going to assume that that person is average and use the worker-independent model. And notice that our system is able to benefit from offline updates given the new data. So here are some key statistics for our costs. For the model learning, we spend a total of $21. And for the execution on this image description task, our agent spent an average of 46 cents per image description. And we give 20 image description tasks on Mechanical Turk, and we're comparing 2 workflows. One is the workflow generated by our decision engine, and the other is a static workflow. And here we're comparing the ultimate result if they're spending the same average cost. And notice that there are more data points to the right of the line y equals to x, which means our dynamic workflow generates higher quality compared to a static workflow.
Statistically significant?
Yes, it is significant, statistically significant. That's the next thing I'm going to say. Okay, and then we're going to compare the average quality of the 2 workflows. We find that a static workflow generates an average quality of around 0.6, whereas for Turkacho we get around like 0.67, which is around like 11% more quality, which doesn't sound to be too much. So we perform additional experiment, that is to keep running the static workflow until it reaches the point that it's going to get the average quality of our dynamic workflow. And we find that to catch up with this 11% more quality, we have to spend over 28% more money. This is because quality improvement is not linear in the cost. And we want to find out why our dynamic workflow works better. So we check the execution logs, and we find that for 7 images, the dynamic workflow actually performs fewer improvement iterations. And actually 6 of them are actually having a better and higher quality. So this shows that our system is able to track the quality perfectly. And at one time, the system tend to trust just the first voter because that worker was known to be a very good voter. And most interestingly, our system is able to make intelligent ballot use, as Etsy pointed out. So if for static workflow, it either gets 2 or 3 votes at every single iteration. So the average ballot per iteration is pretty flat. However, for our system, it chose to not to do any ballot for the first 3 iterations because improvement at that time is really easy. Whereas as the iteration number increases, it chooses to do more and more ballots. It's because improvement is really hard and we really want to guarantee the quality there. The only exception is that at the 8th iteration, the number of ballots drops. Can you guess why? Because at that time, the improvement is really too hard, and only the first person says, no, this is not an improvement. We tend to believe that.
But the average quality is 67, right?
Yeah.
So that means there's a 1 in 3 chance that a random person can improve it.
Right.
So does that mean the process is done? I mean, there must be a stop. There must be some sort of stop. Oh, is it the cost stopping criterion?
Yes.
I see.
What is the measurement for quality here?
What is the
Quality, how do you measure the quality of an outcome?
So the quality here is determined by our model. So we have this conditional distribution function, right?
So in your bar graph, when you are giving the static and the dynamic policies and comparing their qualities here, is it the quality inferred by the system or is it the quality that you measure by looking
Oh,
at
yeah, that's a good question. So we give this to mechanical Turk graders and ask them what is the quality of the artifact. Yes.
So,
Yep.
have you taken any adversarial view of this and said, if I only care about manipulating a small number of items, right, I can basically do good work until you give me something that I want to manipulate and then manipulate it. So have you thought any about analyzing how susceptible this is to that type of adversarial behavior?
Sorry, I didn't get your question.
So in a lot of these crowdsourcing tasks, you want to actually prevent against adversaries manipulating what you think is the truth, right? So one way to exploit this type of thing is for me to essentially do good work, right? You start estimating that I'm a good worker, and therefore you need to ask for less backup on my advice, right? Now I see something I want to manipulate, and I've sort of built up the credits to do it. And so I just do it, and now you don't ask for enough backup, and you go with it. So I'm actually able to get away with a certain amount of manipulation without you ever questioning that.
Sure. And I think that's going to be catched up by our update of the system, because as we're getting more data from people, we're going to perform offline update based on the previous performance of that people. So if a person previously gave us a lot of good answers and correct answers at the beginning, then we have a belief that that person is pretty good. But afterwards, if you're give us like bad answers, for example, if a lot of other people disagree with you, then we're going to slowly decrease our credit in you.
I didn't quite follow this. I think you said that basically you weren't going to ask for backup labels on good workers. So how do you actually end up catching that?
So
if I'm a good worker, how do you know to go out and do that and still get the cost savings?
So for example, here, if you are eliciting an average of 7 votes, right? And previously we think that you are a good voter, and we trust you more, right? And if you disagree with all the rest of the people, then we think that, or at the end, that we think that you're actually making a mistake here, then we're going to incrementally discredit you a little bit, right?
guess part of the question is or in addition to that question is it observable? Is your estimation of a worker's quality in any way observable to them? Like, do they see their reward go up? Because the more that it's observable to them, the greater the risk for that kind of gaming becomes, right? Because like if I can see like, oh, my reward is getting higher and higher and higher, they must really like me, and now I'll slack off or something, right? As opposed to if everyone gets a flat reward, and you never know anything like how many people are voting on this particular round or something like that. The less you keep that information away, the harder it is for the person to game the system probably.
I see. Okay.
Are you really optimizing the reward?
No,
or
we're
is
not.
it just the selection procedure that's affected by the quality control?
We're not doing any like dynamic rewarding.
So the reward's fixed.
Yeah, it's
The
fixed.
It's the same. I see. So that kind of it hides it a little bit, I guess. They don't know how.
Still, you have the problem that the confidence. So if I play long enough as a good guy, maybe you'll get to the place in which you don't question my labels anymore, right? And then you can no longer catch the fact that I became a malicious player.
Yeah.
So it's like in what happened in boosting, right? This is why you have to want to limit the weight you put on every single example and stuff like that.
I think here the real challenge is in a mechanical track system there are just so many users. Not being picked by me doesn't really matter that much for the worker if you are getting a fixed reward. Then I'll just give you the easiest answer that I can give and collect my reward and get out of the system.
Yeah.
You're saying you'll just find another task or
I'll
something?
find another task.
There's still a cost because if you get marked as there's a lot of tasks where you can mark that you want people with at least this much accuracy rating from previous tasks. So, I mean, worst case, they can always start another account, but there's some pressure you can put on them. I mean, there is a little bit of negative that you are putting in them by marking them as
Sure. I think that's a really interesting question. Whether people are going to give you the truthful answer, based on like the money that you're going to give them. Yeah, I think that's really interesting too.
I mean, one point, just in reality, I mean, if you ever run sort of the big sets for your own game, I mean, the way that you generally do the filtering, besides the post hoc manipulation of labels, is you do qualifications and you do bonuses and honeypots, and the combination of these three is generally fairly effective for sort of weeding out the bad apples, and then the task after that is really getting around the sort of real disagreements between them.
Right.
Just why, sort of going back to why Hill model that work. And then, sort of, is there a way for your models to take into account the fact that you could also design, in the design, you could incorporate schemes for qualifications or bonuses, or?
Yeah, we can certainly do qualification tests. Yeah, that's possible way of doing that. Yeah.
But in the
We haven't done that yet.
Okay.
So the voting was binary, people given the choice of A or B. Would it be valuable to actually give people the third option, which is I don't know, so you potentially get information? So you can imagine a situation where you have low I don't know, high I don't know, and then but you still have the same.
Yeah, that's another option we also considered when we do this task. But we're going to, first of all, it's going to be very useful potentially, and then it might complicate the task itself because we might need additional models for that. And I was afraid that a lot of people might just keep I don't know, and that's going to give us no information. So it's a trade-off. Yeah. Okay. So related work. So I'm going to briefly maybe mention the first one. So Eric has done writing the general computation paper, and his idea is that all aspects of the workflow can be crowdsourced, ranging from decomposition and controlling, designing, things like that. And there are many other interesting related work. And I want to mention that all those related work are very new, which means the area is really new and hot. So I want to spend a minute maybe just mentioning my other work and decision making. So I have two state-of-the-art optimal MDP planners. One that solves the problem much faster, and the other solves much larger problems than have previously attempted. And I'm very excited to talk about those, but I don't have time. And also for the ranking policy, project, I provided the decision maker with an ordered list of suboptimal policies, which gives the decision maker the flexibility to choose the most appropriate policy based on maybe other criteria. Okay, some future work. So first of all, there are many interesting next steps for this work. So first, a lot of requesters, they really want to attract the best people to work for them, the most accuracy workers for work for them. And one way is to do to build an incentive system. And Amazon Mechanical Turk really gives us an option to give us bonus to workers. And the question is that when to give such a bonus and how much the bonus should be. And we might also want to investigate maybe other recognition systems such as leaderboards. And also, I want a system to also incorporate some time-constrained tasks. And therefore, we want to study the relationship between the amount of reward and the response time so that we can better trade off completion time and the cost. And also, if we can also do dynamic pricing in order to meet certain deadlines. And to get the best information, as Kevin also pointed out, we might want to relax ballot questions to multi-value questions, and then maybe just ask people's confidence levels for those questions. And my work has been done just to help requesters, but on the other side, we also want to help the workers. And here is the current homepage for Amazon Mechanical Turk workers. It contains some useful information, for example, the number of hits you approved, bonus, total earnings, etc. However, it doesn't capture a lot of other really interesting questions that workers really want to know. For example, what are the reputations for the requesters? Are they really fast at paying people? Do they really reject a lot of work for those workers? And also some interesting recommended hits so that we can build possibly a recommendation system for the workers. And workers might want to know what other people are working at. So want to know what are the popular hits available on Mechanical Turk. And hopefully in this work I have convinced you that artificial intelligence is useful for the specific workflow that is iterative improvement. But not all workflows are iterative improvement. But I want to argue that actually every workflow is going to need AI, because we need AI for optimal pricing. We need AI to study and learn the parameters of the model. And we need AI to do decision control and possibly choosing the best workflow among a number of workflows for a particular task. So my long-term goal is to build a self-adaptive quality control system for Mechanical Turk. So it should be beneficiary from the following components. For example, there are some new tasks, and therefore we need new decisions. And our system should be useful if it is able to detect and predict spammers automatically. And also, it's interesting to learn a temporal model for the workers, because the workers' performance tend to vary along time of day and day of the week. And I've talked about a special type of task, which is English description of image. So what about the other tasks? How do we efficiently transfer the model from one particular task to another task? Let's say audio transcription or natural language translation. How do we do that? Also, our system should incorporate an effective incentive system so that we can attract the best workers to work for us. And that will be interesting work in matching workers with tasks. And my expertise is in decision making under uncertainty, so I'm also generally interested in other applications. So, for example, Bing has described itself as a decision engine, and I believe that Microsoft has a lot of data on user query logs. So, how do we use this huge amount of data to understand people's intentions? How to how to return the best and most relevant information back to the people and use that information to better serve people and potentially targeting people with advertisements. And social networks is another interesting and enthusiastic area that a lot of people are using it every day. So it'll be interesting to study how people make decisions on social networks and also how to combine social networks with crowdsourcing. I think Prague and Matt have done some interesting work showing that people who interact with each other more often on social networks tend to have similar interests. And Eric has done some friend sourcing work, which is a social network version of crowdsourcing. And I really want to find out how do we use this information to build a better worker model. So in this work, we proposed the first decision-theoretic quality control system for crowdsourced workflows. And we propose efficient mechanisms of learning the model of the system and plugging the learned model into an end-to-end system that is able to achieve statistically significant better results. And the system is able to incrementally updating the model itself given the new data. So finally, I want to acknowledge a lot of help for this work, and I also want to thank you all for your attention.
Any other comments or questions? It was a nicely interactive session. Thanks a lot.